Hello students, today we will discuss about the exception handling in pipelining. Last session we were discussing about what is pipelining, what are the features of pipelining, how pipelining can be implemented for the execution of various instructions present in MIPS microprocessor architecture. So today we will discuss about exception handling in pipelining. So what is an exception? As you know, exception is something that happens between the execution of a program or a set of instructions that may happen dynamically or that may affect the normal flow of execution. That is normally for a program it is not related to the syntax and all, it is strictly depending on some other exceptional situations that we cannot control. So similarly, when we are having different instructions being executed in parallel, the same situation may also occur. That means there is a chance of having a number of exceptional situations. So what is an exceptional situation in pipelining? So it is a situation where the instruction execution order is changed in an unexpected way. So the normal order of execution, so as you know, in pipelining we are having different instructions that are being pipelined in different stages, and different stages of each instruction will be under execution at a particular moment. So if it violates that normal execution order that is being changed due to some unexpected situation, we can call this situation as an exceptional situation. So it is very difficult to handle, especially in a pipelined processor, because the overlapping of instructions make it more difficult to know whether an instruction can safely change the state of the CPU. So as we are following a pipelined architecture, that is one after another the instructions are being overlapped, so it is difficult to handle the exceptional situation that happens in between the normal flow of these instructions. So normally for an exception we need to identify the exception, and accordingly we need to have an exception handling mechanism to be provided. So in the case of pipelining, it is difficult to identify that exception, and even for making an exception handling mechanism for controlling or to get back to the normal flow of the execution is a very difficult task in the case of pipelining. So that is a challenge that we are facing when we are implementing pipelining in various processes. So we will see in detail about the different things related to the exception handling in pipelining. Now in a pipeline CPU, as you know, the instructions are executed piece by piece, means each instruction, each stage will be executed one by one in parallel, and it is not being completed for several clock cycles. So it is strictly depending on the size of the instruction and the number of instructions present in the system that is currently under execution. So different pieces of each instruction will be executed in parallel one by one. If you are having some thousands of instructions available, and if they are executing in parallel, we actually don't know how many instructions and how many pieces of these instructions are being executed at the same time. So as you know, for the completion of all these entire instruction, usually it will take a lot of clock cycles. Now similarly, other instructions in the pipeline can raise exception that may force the CPU to abort the instruction. So similarly, if these set of instructions are being executed in parallel or in an overlap manner, there are some instructions that are in the pipeline that can raise some exceptions that will force the CPU to abort the instruction. That means sometimes we need to stop the entire execution of that instruction, and maybe sometimes there will be some delay, there will be some stall that is being generated in between different instructions, and there will be a lagging of the execution of several instructions, and accordingly the entire pipelining will also be delayed. So we cannot complete the entire pipeline procedure within the scheduled time. So there will be a lot of delays if we have got some exceptions in between the execution of these instructions. So let us see what are the different types of exceptions that are available, or that is part of the pipelining. So the major exceptions are like the IO device request. Sometimes if some instructions is actually requiring for some input or output device, and if it is not available, there will be some exception that will be raised, and there will be a lagging of the entire execution of that particular instruction. Similarly, if there is an invocation of an OS service from the user program, if some OS command is being given by the user, and the normal execution to be stopped for that particular moment, so that is another type of exception. Then another exception is tracing instruction execution. So like when we are executing a C program and we are tracing the instruction, or we are tracing the instruction execution order, so tracing the instruction one after another, and in between that tracing there is a chance of the exception. That means unfortunately, or there will be a delay, or there will be a lagging or a stoppage of the normal execution of program. And user defined breakpoint can also stop the execution of an instruction present in a particular pipeline. Similarly, these are only some examples of the reasons for the various exceptions, like integer arithmetic overflow. If some overflow happens between or within the execution of an arithmetic operation. Similarly, a floating point arithmetic anomaly, some issues, some anomaly or issues related to the floating point arithmetic operations may also cause some exception to be raised. Similarly, another exception is the page fault. If some memory access is being done, or if the instruction is actually requiring a memory, and if that memory page is not available, there is a chance of page fault will also make the instruction to be stopped for some time, and will affect the entire set of instructions present in a pipeline. Similarly, an access to a misaligned memory. Misaligned memory means if the memory is not being mentioned based on bytes, if it is not based on byte ordering, and if we are accessing some content that is present between 2 bytes, it is called as misaligned memory. If unknowingly somebody is trying to access the memory in that format, that will make an issue, and it will also produce an exception which is called as misaligned memory access. Then memory protection violation. So when we are dealing with memory and when we are trying to access some data from memory, there are some memory locations that are being protected. So assume that this is a protected memory area, and unknowingly if we are trying to access that memory area, which is actually create an exception called as memory protection violation. We are not having a permission to access that protected memory area. Then another type of exception is using an undefined or unimplemented instruction. Means the instruction is given in a wrong format that cannot be understandable by the system. So that situation, the normal pipeline flow will also be stopped, and it will affect some other instructions also present in the same pipeline. Similarly, if some of the hardware, whatever it be, it may be an input device, or it may be the CPU, or any of the functional units present in the CPU, if that is being or if it is not working properly, or if it is being function means a malfunction happens with the hardware, so automatically it will affect the given instruction also, so that will also create an exception. And finally, if some power failure happens during the execution of an instruction, if some power failure on a particular functional unit happens, that also will affect the execution of a particular instruction. And automatically, if one instruction fails, it will affect other instructions also, because most of the time many instructions are depending on another instruction also. So if one instruction fails, it may affect other instruction also. So automatically the entire pipelining or that parallel execution, that outcome that we are getting because of this pipelining will be reduced due to the occurrence of various exceptions between the instructions that are simultaneously or parallelly executing, that is part of the pipeline. So these are the various types of exceptions that are normally affected on a particular pipeline architecture. Now we'll see some more details regarding these exceptions based on the comparison of various processes. I will take comparison on IBM 360, then VATS machine, Motorola, and Intel 386 series of processes. So the exceptions we are going to specify. I'll just provide some of the examples. We cannot explain all these in detail, but just have a comparison between different machines on all the previously explained exception types. Like first one, IO device request. In IBM it is like some interruption on input and output devices, and in VATS machine it is called as device interrupt, and in Motorola it is usually called as exceptions from 0 to 7 level 0 to 7 auto vector, or that is the exception that happens with the Motorola machine. And in 80386 this IO device request exception is usually mentioned as vectored interrupt. So in various machines it is termed in different names. So another example, another exception type is invoking the operating system services from the user program if the user provides some OS service. In IBM it is called as supervisor call interruption. In VATS it is called as exception, normal exception. It is like a supervisor trap. Then in Motorola it is called as exception, that is unimplemented instruction. And in Intel 80386 it is called as INT instruction. It is interrupt due to the operating system service that is being called by the user. Then tracing instruction execution, it is not with IBM, and in VATS it is called as exception trace fault. Then in Motorola it is called as trace, and in Intel 386 it is called as single step trap interrupt. Then breakpoint, in IBM it is not applicable, in VATS it is breakpoint fault, in Motorola it is illegal instruction or breakpoint, and in Intel also it is called as breakpoint trap. Then integer arithmetic overflow or underflow, it can be an overflow or underflow. In IBM it is called as program interruption, overflow or underflow exception. In VATS it is called as integer overflow trap or floating underflow fault. In Motorola it is called as floating point coprocessor error, and in 386 it is called as overflow trap or math unit exception. So all these exceptions are called by using different names in various microprocessor machines. In that is page fault, it is not applicable in IBM 360. From 370 onwards only these page fault exceptions were treated in IBM. Then for VATS it is called as translation not valid fault. Then in Motorola it is called as memory management unit errors, and in 80386 it is called as page fault. Then misaligned memory access, in IBM it is called as program interruption, that is specification exception, and it is not applicable in VAX. And in Motorola it is called as address error, misaligned memory, it is called as address error, and in 386 also it is not applicable, because in Intel series and all it is not allowing the access to, or misaligned memory access is never being permitted. Then memory protection violation, in IBM it is called as protection exception, in VAX it is called as access control violation fault, in Motorola it is bus error, and in 386 it is protection exception. Then undefined instruction, in IBM it is called as operation exception, in VAX it is called as opcode privileged or reserved fault, and in Motorola it is called as illegal instruction or breakpoint, and in Intel 80386 it is called as invalid opcode. If the opcode, the instruction opcode is given wrongly, it is usually called as invalid opcode. Then if some of the hardware is not functioning properly, in IBM it is called as machine check interruption, then in VAX it is called as exception machine check abort, then in Motorola it is called as bus error, and in Intel 80386 it is not applicable. These type of exceptions are not applicable in Intel series. Then finally the power failure, in IBM it is called as machine check interruption, in VAX it is urgent interrupt, in Motorola it is specified or it is not applicable, and in the case of Intel 80386 it is called as non-maskable interrupt. So these are the various exception events that may happen with a pipelined processor machine, and these are the types of events that are specified. Specific names are given for each of these microprocessor machines. So in different machines different types of exception events are named in different ways, and some of the machines they are not even applicable. So this is only for giving some example types of exceptions present in various machines based on the different types of exception events. Now basically we can categorize these exceptions into different types. The first category of exceptions are general categories. They are differentiated in synchronous versus asynchronous exceptions. That means we are having synchronous types of exceptions and asynchronous exceptions. So the first category is based on synchronous versus asynchronous exceptions. So what are synchronous and what are asynchronous exceptions? If the event occurs at the same place every time the program is executed with the same data and memory allocation, this exception event is called as synchronous exception event. So these portions are very important. The different types of exceptions means the different categories of exceptions. So previously we were describing about the different types of exceptions that may happen. Now the same set of exceptions, the same types of exceptions are categorized based on different situations. So the first category is synchronous versus asynchronous. So what is synchronous exception? If the exception occurs at the same place every time the program is executed with the same data and same memory allocation. So in every situation, if the exception happens with at the same point, the same situation in the same time with the same data and same memory allocation, it is called as synchronous exception. Now the asynchronous events are caused by devices external to the CPU and memory. So any exception that happens because of some other devices that are external to the CPU and memory, that is called as asynchronous events. So if any exception that happens with the program and its related data and memory, it is called as synchronous. And if it is not related to this program, data and memory, or any other devices external to the processor and memory, or it can be anything, it can be a power failure, it can be or something that is outer to the internal CPU and memory, that is called as asynchronous exception events. Now the second category is, so we are totally having 5 categories. Now second is user requested versus coerced. User requested versus coerced. Now as the name indicates, if the exception happens because of some user interaction, it can be called as user requested, and the opposite is called as coerced. Okay, so if the user of the task directly asks for it, it is a user requested event, or it is also called as predictable exception event. If the user is providing, like it is providing an instruction to trap, that is called as user requested exception. Now coerced exceptions are caused by some hardware event that is not under the control of the user program. So if something happens because of some hardware malfunction and all, can be coming under the category of coerced exception type. So user requested, it is because of some interaction from user to the system, and coerced, that happens automatically without having any interaction of the user. So it is not predictable. So predictable means if I am providing an instruction to trap, to stop, it is called as predictable or user requested event. And if it is not being predictable, that means it happens automatically because of some issue related to the hardware, it is called as a not predictable or coerced exception. Then third category is user maskable versus user non-maskable exception. If an event that can be masked or disabled by the user, it is called as maskable. If an exception can be disabled, if a user can control the usage of exception, can be called as maskable exception. And if it is not, it is called as user non-maskable exception. So if any of the exception can be controlled by the user, or it can be disabled or enabled by the user, it can be called as a maskable exception, and the opposite is called as non-maskable exception. Then fourth category is within exception versus between exceptions. So within instruction versus between instructions. So what is within instruction? That means if any exception happens, or if any exception is being raised within the instruction itself. If it happens within the instruction, it can be called as within exception. And if it is happening between two different instructions, if it is between an instruction A and instruction B, it can be called as between instruction exception. So some of the exception may happen within the same instruction itself, and some of the exception that may happen between, after completion of one instruction and before the starting of second instruction, that is called as between exception. So that is the fourth category. And the fifth category is called as resume versus terminate. If the program's execution always stops after the interrupt, it is a terminating event. If an exception occurs and because of some or after some time, if it can be continued, it can be called as a resume exception. It can be continued, But if an exception happens and accordingly the entire execution will be terminated or that will be stopped, that exception can be called as a terminate exception event. So resume exception and terminate exception, so all these are considered as events. So based on several events, so because of some events only this exception happens. So all the events that produces the exception that can be resumed even after the occurrence of exception, that is called as resume exception. And if it cannot be resumed after the occurrence of exception, it is called as terminating event, terminating exception. So these are the 5 categories. Once again I will just read it out. Synchronous exception versus asynchronous exception, user requested exception versus coerced exception, user maskable exception versus user non-maskable exception, within exception versus between exception, finally resume exception versus terminate exception events. So important 5 categories of exceptions. So the same types of exception itself is being categorized into 5 different groups, and in all these 5 different groups we are having 2 more categories. So totally we are having 10 types of exceptions or 10 categories of exceptions available. So we will see some of the types of exception events, and let us see in which type of exception that is. So we are having all these 5 categories given in the x-axis here: synchronous versus asynchronous, user request versus coerced, user maskable versus non-maskable, within versus between, and finally resume versus terminate. So these are the exception types that we have already mentioned. So IO device request, it is synchronous. So you can simply imagine the meaning of all these categories. It is asynchronous, coerced, non-maskable, between, and resume. Operating system function invocation, it is synchronous, user request, non-maskable, between, and resume. Then tracing, synchronous, user request, user maskable, between, and resume. Breakpoint, synchronous, user request, user maskable, between, and resume. Arithmetic overflow, synchronous, coerced, user maskable, within, and resume. Floating point arithmetic overflow or underflow, it is synchronous, coerced, user maskable, within, and resume. Then page fault, synchronous, coerced, non-maskable, within, and resume. Then misaligned memory, synchronous, coerced, user maskable, within, and resume. Memory protection violation, it is synchronous, coerced, non-maskable, within, and resume. Then user defined instructions, synchronous, coerced, non-maskable, within, and terminate. Then hardware malfunction, asynchronous, coerced, non-maskable, within, and terminate. And finally power failure, asynchronous, coerced, non-maskable, within, and terminate. So you can easily compare. So why IO device request is asynchronous? You can easily imagine why breakpoint is resume type of exception, why page fault is coerced, why a hardware malfunction is non-maskable, why power failure is terminate, etc. So all these answers are easily captured by using this particular table. So all the general exception types are being compared based on the 5 different categories that we have already mentioned. So this is also very important. So the general question is, what are the different types of exceptions? So these are the basic types of exceptions. So these are the types of exception, and these are the different categories of exception. So we are dividing the same set of exception into 5 different categories, and each category we are having 2 types, and all these are coming under any of these different categories of exception type. I hope it is clear. Now stopping and restarting execution. So there are some situation we can stop the instruction due to the exception, and sometimes we need to restart the execution from the place where it was actually being stopped. So as in unpipelined implementation, the most difficult exception have two properties. Normally they will occur within the instruction. So if an exception occurs within the so this is an instruction, and if an exception occurs within the instruction, that will create a problem. So if something happens in between, we should resume from the same point. That is a major challenge. So they occur, normally it will happen, they will occur within the instruction, and they must be restartable. It should be restartable from the point it was stopped. So for an example, if you take a virtual memory page fault. So page fault is if a particular memory a page is not available when it is being requested in between a particular instruction. It will result in a data fetch cannot occur until some time in the memory stage of the instruction. So by the time that the fault is seen, several other instructions will be in the execution. So later when it receives that page, so in the same time some other instruction will be executing and some other will be using the same page. So in between the instruction execution, it is actually given for a page request, but page is not available means a page fault occurs, and the instruction need to wait until that page is available. So until that time this instruction will be waiting and some other instruction will be executing in parallel. But if one instruction is waiting for some time, it will affect the entire time, means the entire execution of the entire pipeline instructions, because if one instruction delays, it will affect the overall set of instructions present in the pipeline. Now the page fault must be restartable and requires the intervention of another process such as the OS. So how the page fault can be handled? So as you know, in operating system we have already studied about how to handle page fault. So if a particular page is not available, some automatic execution that happens with the control of operating system for handling page fault means that is to be taken. So sometimes if it is not directly available, OS will be doing based on some strategies, it will take the data from the secondary memory and bring it to the primary memory for the current execution, and that to make the page available, the OS need to do some additional operation. So it is usually being so in between the instruction a page fault occurs, so automatically OS must provide the corresponding control for or corresponding solution for the occurrence of page fault. So automatically what is happening is the current pipeline which is having the page fault problem, it will be safely shut down and state saved so that instruction can be restarted in the correct state. So when the page is not available, what is happening internally is the pipeline that is currently under execution will be safely shut down temporarily, and the current state will be saved so that it can be continued, it can be restarted in the later stage after it receives the corresponding page that was actually being given request. So restarting is usually implemented by saving the program counter of the instruction at which to restart. So program counter usually holds the address of currently running instruction. So if the current instruction fails, that program counter to be saved, that is to be saved, and later it is to be referred to the instruction or the program counter, and from there the system need to continue with the we need to restart the execution of the remaining portion of the same instruction. Then if the restarted instruction is not a branch, so if the same instruction is being stopped in between, and if the restarter instruction is not a branch, then we will continue to fetch the sequential successor and begin their execution in the normal function. So if that instruction in between, if it is being stopped, and just after that we need to restart. Okay, so if it is a normal sequential set of instructions, it can directly continue with the next sequence of statements. But if it is a branch, if the restarter instruction is a branch, then we will re-evaluate the branch condition. So once again the condition to be evaluated, and accordingly it should go to some other location and begin fetching from either the target or the fall through. So sometimes based on the condition, sometimes the condition may be varied, or according to the, so anyway when we are restarting a branch instruction, we need to re-evaluate the branch condition once again, so that it can correctly go to the next instruction according to the branch condition. So if it is just a simple normal sequential instruction, it can directly go to the next set of instruction after the current instruction. But if it is a branch, it should re-evaluate the already existing condition that is part of the branch statement. So that is to be taken care. So here the only differentiation is between a branch instruction and a non-branch instruction. So branch instruction to be given additional care for re-evaluating the condition that is part of the branch statement. Then when an exception occurs, the pipeline control can take the following steps to save the pipeline state safely. So we are just continuing with what is happening if an exception occurs in between the pipeline. So we are having an entire pipeline set of instructions available. They are executing in parallel in an overlapped manner in the form of a pipeline. So we should have an overall pipeline control in between. So in any of the instruction that is present in between this pipeline may produce an exception. So what are the steps to be followed when an exception happens within that entire pipeline? So first thing is, when an exception occurs, force a trap instruction into the pipeline on the next instruction fetch. So if one instruction is got an exception, so automatically we need to have some control. So next set of instruction, maybe some of the instructions are depending on the previous one, or sometimes the next instruction will be an independent instruction also. Whatever it be, it should force a trap instruction into the pipeline on the next instruction fetch. So currently some instructions are on some or it's part of execution, but whenever the next instruction fetch occurs, there a trap instruction that is to be forced before taking the next instruction fetch. So until the trap is taken, turn off all writes. So in this situation, so if an exception occurs, many things may happen, many wrong data, many wrong evaluation may happen. So it is always better to turn off all writes for the faulting instruction. So if this instruction fails in between, it will just turn off the write. So some write means because of this instruction some data will be written. Because of this instruction some data will be taken or read. So normally write is the main issue, that is the exclusive one. So it requires the turn off of all the writes for the faulting. So this is the faulting instruction, and the write must be turned off when an exception happens on that particular instruction and a trap is being forced, and during that at the same time the write of that particular instruction must be turned off, and for all instructions that follow in the pipeline. Okay, so it is not only for the current instruction, it will produce or it will turn off the writes for all the instructions that follows the same instruction, because the following instructions may affect the current instruction data. Maybe all these instructions are depending on the data of the result of this particular instruction. So until the trap. So if a trap is being forced, put a write a lock or turn off the write of the current insertion and all the following insertion, and when it is to be maintained until the trap is taken. So after some time, after the maintenance, sometimes it will be taken off, so that time it can be returned. So these turned off writes can be again come back to the turn on stage. So okay, so until the trap is taken, turn off all writes for the faulting insertion and for all the insertions that follow in the pipeline, and this can be done by placing zeros into the pipeline latches. So it is just like having the set of insertions given here. So this is the insertion where the exception occurs, then just put a 0 in the pipeline latch. So the following insertion, there also put a 0. So whichever, so for every pipeline latches there will be an additional bit for placing a 0 that indicates that some insertions before or the current insertion is having an exception. So by looking at the pipeline latch, we can assume that what is the status of all these insertion, whether that is currently under execution or whether it is affected by an exception. So all the exceptional insertions and the following insertions must be having a 0 being placed at the pipeline latches that is present in the remaining pipeline. Then after the exception handling, so we should have some exception handling routine in the operating system, just like the page fault. When the page fault occurs, so what will be done? The current insertion will be given a 0 at the end of the pipeline latch. Similarly, all the following insertion will also be given 0 at the end of the pipeline latch. So then what the OS will do? Then the OS will do the solution for that exception. That is, the exception handling routine will be executed by running the operating system page fault. Some of the page fault paging algorithm will be applied, like page replacement algorithm will be applied. Accordingly, it will make the data or page available to the system. So after that exception handling routine in the OS receives control, it will immediately saves the program counter of the faulting insertion. This value will be used to return from the exception later. So it will do all these operations when an exception happens. So when an exception happens to a particular insertion, it will stop that insertion, put a 0, means indicates all the writes are being logged for the current insertion and for all the following insertion. Then the OS will get the control, or it will get the program counter, and it will save that program counter, and it will handle the exception. And when it comes back to the same insertion after having the exception is being handled, the same program counter will be referred again for continue with the same insertion, and that time all the write lock will be removed. So after the exception has been handled, special instructions return the processor from the exception by reloading the PC and restarting the insertion stream. So this is what I was mentioning. So after the exception has been handled, so after for a page fault, there will be some page replacement algorithm that will be invoked by the operating system, and that is being handled. Now currently page is available. Then it will give special instruction that is used to return to the processor from the exception by reloading the PC. So take the previous PC itself and it will restart the insertion again. Now if the pipeline can be stopped so that insertions just before the faulting insertion are completed and those after it can be restarted from the scratch, the pipeline is said to have precise exceptions. So there are some exceptions if that happens. Once again, if the pipeline can be stopped so that the insertions just before the faulting insertion are completed. So somewhere some fault happens and all the insertions before that fault have already been completed, and those after it can be restarted. So some insertions occurred before, then some exception occur here, and there are some more insertion followed, and this is being completed, and some exception happens here, and after that it can be continued with the following set of insertions in a normal fashion. It can be called as precise exceptions. Once again, if a pipeline can be stopped so that the insertions just before the faulting insertions are completed, and those after it can be restarted from the scratch, the pipeline is said to have precise exceptions. Now let us look at MIPS processor. We'll see the exceptions in MIPS processor. So as you know, the different pipeline stages of MIPS architecture are insertion fetch, insertion decode, execute, memory for load and store, and finally write back to the register. So these are the different stages of pipeline, and the different exceptions that may happen between the different stages. So during insertion fetch, we can have a page fault on insertion fetch, then we can have a misaligned memory access or memory protection violation, because we are going to access the memory. So insertion fetch is always dealing with the memory. So any errors or exception related to the memory may happen during insertion fetch. And during insertion decode, it will be if the insertion is undefined, insertion is wrong, or it is an illegal opcode. During insertion decode, there is a chance of exception. Then in the execution stage, it is usually happens with the normal arithmetic related exceptions. Then the memory stage, that is with the load and store operation for data memory. So that situation, what is happening is, again it is dealing with the memory. So the same thing that was happening before, like page fault, then misaligned memory protection violation, etc. The same thing that was with insertion which fetch will also be happening in the memory stage also. And during the write back stage, normally there is no chance of it's because this is the final stage. From EHC we are actually producing a result, and in the memory stage we are producing the data value. So even if we are having some problem with write back, we can get the data from EHC or memory stage. So that is why we are not dealing with the exception that is happening with the write back stage. So you might be remembering what is this forwarding and all. If some error happens, some clash happens with this additional other part of the pipeline, the result can be forwarded to the next stage without writing the final result into the register file. So that is why we are not giving importance to the exception of write back stage. Then with pipelining, multiple exceptions may occur in the same clock cycle because there are multiple instructions in execution. So there is a chance of more than one exception that may happen within the same clock cycle if we are having a number of instructions being executed in parallel. So the pair of instructions given below can cause a data page fault and an arithmetic exception at the same time. So this is an example. Two operations, a load and addition operation is given, and they are in a pipeline architecture. Insertion fetch is dealing with memory, insertion decode, and for the first insertion, same time next insertion fetch, then execute, then insertion decode of the second, memory execution of the second, then write back, it's memory stage of the second, then the write back stage of the second insertion. So during this simple two insertion in a pipeline format in two different stages, here also you can see that there is a chance of for example two exceptions that may happen at the same clock cycle. So these are clock cycles: first clock cycle, second clock cycle, third, fourth and fifth. Then totally it takes 6 clock cycles. So two exception may happen at the same time. For example, a page fault, if like what you say, some arithmetic exception and memory. So look at this stage, memory, and so memory related exception may happen at the same clock cycle, or some arithmetic exception may happen at the same stage. It may also happen the same clock cycle we can have. So if you are having some multiple number of instructions at the same time, at the same clock cycle itself we can have more than one exception that may also occur. Similarly, with other stages also we can have the possibility of the same situation. So this can be handled by dealing with only the data page fault and then restarting the execution. So when this happens, that means more than one exceptions at the same clock cycle, we will be dealing with only the data page fault and then restart the execution again. So primary importance is given to the page fault related to the memory. So that is one solution for having the same same size clock cycle. We can have the possibility of multiple occurrence of exceptions. Similarly, exceptions may also occur out of order, means two different situations that is usually happening. So means in one cycle one exception may happen, next cycle another exception may happen. That is called as out of order exception. So since we are implementing precise exceptions, the pipeline is required to handle the exception caused by the load instruction first. So we are dealing with the precise exception. That means some instructions are already being completed and an exception occurs, and some instructions are yet to be executed. So that is to be completed in a normal fashion. So that type of exceptions only we are considering now. So the pipeline is required to handle the exception caused by the load instruction first. So if some out of order exception happens, we are actually trying to handle the exception that is caused because of the load instruction, that will be given the priority. So if two exceptions happen simultaneously, it will be given the importance to the page fault exception, and if it is a precise exception, it will be given importance to the load instruction first. Then the hardware posts all the exceptions caused by a given instruction in a status vector associated with that instruction. So as I was mentioning before, the same pattern we are explaining once again. With each instruction, it will be executed in parallel in pipeline manner. Then there will be a corresponding hardware for the solution of this exception, for identifying the exception and have a resolution. So the hardware, some hardware that is with that pipeline architecture will post all the exception caused by a given instruction in a status. So every instruction will be having a status vector that holds that will be holding some value that decides whether the instruction is executing properly or it will be having some exception. So every instruction will be having a status vector, and by looking at the status vector, all other instructions can understand whether everything is working properly. The exception status vector is carried along as the instruction goes down the pipeline. So when it goes down, it will be carried. Status vector will be carried. So first instruction, when it goes to second, then when it goes down to the pipeline, it is based on the status vector of the previous instruction only. It is actually continuing with the following instructions. Once an exception indication is set in the exception status vector, any control signal that may cause a data value to be written is turned off. So if this status, as I was mentioning before, this status vector will be having a value 0, indicates all the write will be turned off. I have already explained before that. Okay, so all the data value to be written is turned off. All the writes will be turned off if the status vector shows 0. If any exceptions are posted, they are handled in the order in which they would occur in time on an unpipelined processor. So if any exception happens, if any exceptions are posted, they are handled in the order in which they would occur. So if it was this is the pipeline manner, and this is the instructions that are written in unpipelined manner in the normal fashion. So there will be some sequential order, and if any exception occurs, it will be handled in the order in which it is actually available in, just like an unpipelined processor structure. So So that is all about the exceptions in MIPS. So we have seen pipelining, then the various exceptions. What is exception in pipeline architecture? What are the different types of exceptions? What are the different categories of exceptions? And we have seen some examples of various types and categories of exceptions based on various machines, and we have differentiated different categories of exceptions and how we can handle the exception in various situations in a precise exception and a non-precise exception, and the usage of status vector and maintaining the flow of execution during the occurrence of an exception. And we have also seen the exception handling in MIPS processor and how it can be handled in the MIPS architecture with the usage of status vectors, which is similar to the usage of the zeros and right turn off in the normal execution handling procedure. So we have seen the general procedure for exception types, exception handling in pipelining. So that's it for now. Thank you.